Good morning, everyone. My name is Gonçalo, and I'm here to present one of the projects of my PhD. And in this project, I was analyzing the potential for genomic imprinting to evolve in sexually selected traits. So you will see a lot of lines during this presentation, but this is only for presentation purposes. Okay. So from the theory of sexual selection, we know that males and females have different evolutionary interests. Males want to mate as much as possible, while females prefer to mate with good quality mates, in general at least. So this creates a sexual conflict between males and females, and usually this leads males to develop traits that we call male-harming traits that allow them to increase their fecundity at the expenses of the fecundity of the females that they mate with. One way to reduce evolutionary conflicts between individuals is through kin selection. So from the kin selection theory, we know that there are two big categories of behaviors: selfish behaviors and altruistic behaviors. And we know that the more individuals are related to each other, the more likely they are to manifest altruistic behaviors and less likely to show selfish behaviors. This overlap between sexual selection and kin selection has been ignored for quite some time, but in recent years this started to change, with a lot of research being done on this subject, both empirically and theoretically. And this all started with a work by Rankin in 2011, where he was trying to understand the role of relatedness in changing the sexual conflict between females and males. So I will briefly present the work of Rankin. So he had a theoretical model. In this theoretical model, he had an infinite population that was divided into patches, and within each one of these patches there were males and females. Males and females were going to interact with each other, and during this interaction, males could harm the females. And by harming the females, they could increase their fecundity at the expenses of the fecundity of the females and also of the other males that were mating with those same females. After this interaction, a new offspring is born, and males and females can disperse to different patches at different rates. The important detail here is that by dispersing, individuals will only interact with individuals that are unrelated to them. So then some juveniles die, others reach adulthood, and this starts the life cycle of the model again. So these are the results of the model. In the x-axis we have female dispersal, in the y-axis the level of male harm. And if the rates of dispersal of females and males are exactly the same, we see that there is no effect in the level of male harm. And this happens because we have two factors at play here. So we have relatedness and we have kin competition. As we reduce dispersal, we are increasing relatedness, meaning that the level of male harm should go down, but we are also increasing kin competition, and kin competition increases the level of male harm. So when the dispersal rates are exactly the same, these two factors cancel each other out, and we get this result. But when we have sex-biased dispersal, in this case female-biased dispersal, this no longer happens. There is a disentanglement between relatedness and kin competition. So we see now that by decreasing dispersal, we increase relatedness and the level of male harm goes down. So relatedness is the important factor at play here. If we have male-biased dispersal, we see exactly the opposite. Now by decreasing dispersal, we are increasing kin competition, and now kin competition is the main factor. So this was Rankin's results, and so we conclude that yes, so relatedness can play a role in changing the sexual conflict, but this is more likely to happen when there is sex-biased dispersal. One consequence of sex-biased dispersal is that it may lead to intergenomic conflicts. So what do I mean by this? So each individual has two big classes of genes, maternal origin genes and paternal origin genes. And when there is sex-biased dispersal, these two genes might disagree regarding how the individual should interact with his social partners. So what does this exactly mean? So let's go back to Rankin's model. And now we have, again, female dispersal in the x-axis, in the y-axis the level of male harm. And now we have three different lines. We have a blue line that represents the levels of male harm favored by the paternal origin genes. The gray line, which is the same lines of Rankin's model, and in the orange line that represents the levels of male harm favored by the maternal origin gene. So let's focus on the left side of the figure. Here we have male biased dispersal. This means that males disperse to other patches, and when they arrive to those patches, they will interact with males that are unrelated to them. However, the females do not disperse, meaning that the females are likely to interact with females that are related to them. This means that in the new generation, a new offspring will be less related to the paternal origin genes and more related to the maternal origin genes. And so if we assign control over the phenotype to the paternal origin gene, we see that the paternal origin gene would favor higher levels of male harm when compared to the levels of male harm favored by the maternal origin genes. So this is an intergenomic conflict, and what are the consequences of these intergenomic conflicts? So to answer this question, I developed an individual-based simulation. So in the x-axis now we have generations, and in the y-axis here we have genetic expression, and in the y-axis the level of male harm. So in this simulation I have three big assumptions. I assume that male harm has yet to evolve, that the genetic expression of the maternal and paternal origin genes is going to add up to give the final level of male harm, and that I also assume that genes know where they came from. They know if they are maternal origin or paternal origin gene. So at the start of this simulation, we see that genetic expression increases, because even though they disagree regarding the level of male harm, they still want a level of male harm that is above 0. But then we arrive at this point. At this point, this is the level of male harm favored by the maternal origin gene. This means that now maternal origin gene wants to keep the level of male harm at that specific level. However, the paternal origin genes do not agree with this, and therefore they continue to increase. And this means that for the maternal origin gene to keep the level of male harm at that specific level, they need to do the opposite of what the paternal origin genes are doing. And this goes on, so they start to decrease their genetic expression to counteract what the paternal origin genes are doing. And this goes on until we get to a point where the gene is basically silent. At this point, the paternal origin gene wins the conflict, and it's free to set up the level of male harm that is optimal level of male harm. These kind of situations we call genomic imprinting, when genes act as if they know where they came from, and the usual consequences is that we end up in a situation where one of the parental genes is being fully expressed while the other gene is being completely silent. In this case, the paternal origin gene, but if we have female bias dispersal, we would get exactly the opposite. So now we have an individual that expresses only the paternal origin gene, and we can now start making predictions of what will happen to the phenotype of the individual if this equilibrium is disrupted. So let's assume that there is a mutation in a maternal origin gene. In this case, nothing really happens because that gene was already silent, but let's assume that the same mutation occurred now at the paternal origin gene. Now the individual completely loses its phenotype. In a normal situation where the two genes would be being expressed, the individual would be affected, but the effect wouldn't be that severe. And that's a usual consequence of genomic imprinting, where a normal or a mutation that would just modify slightly the phenotype of the individual, in these circumstances it leads to an extreme form of the phenotype. And we can make similar predictions regarding other types of mutations and changes in the genome, and also when there is female bias dispersal, or when the gene, instead of being a promoter of male harm, it's an inhibitor of male harm. Unfortunately, I don't have time to go through all of this, but you can check the paper out that is already published in Evolution. The important detail here is that by predicting how the phenotype of the individual will change according to these modifications, we can basically give a theoretical tool to empiricists to test for genomic imprinting in these particular types of traits. So the take-home message is that indeed relatedness can change how sexual conflict acts between females and males, but this is more likely to occur when there is sex bias dispersal. One consequence of sex bias dispersal is that intergenomic conflicts might be present, and in those circumstances, these might lead to genomic imprinting. If genomic imprinting is present, we can make predictions how changes in the genome will affect the phenotype of the individuals, and these allow us to understand if genomic imprinting is present or not. Again, if you arrive late, lions are here just for presentation purposes. So I'd like to thank my supervisors, Susanna Varela and Andy Gardner, and also the people in Gardner's lab and the people in the theory lab. And thank you for your attention. Any questions? No? I think that's it then. Thank you.